Hello and welcome to section 8.1, Sequences and Summation Notation with me, Mr. Hain. All right, so we're just going to be building up to some simple definitions at first, and right now we've got some sequences. So what are sequences? Well, sequences usually are infinite, and they can be finite. So there are two different types of sequences. For an infinite sequence, the domain is the set of all positive integers. So it's just the regular counting numbers that you learned when you were in kindergarten, 1, 2, 3, 4, 5, 6, and so on, all the way up through infinity. Now, the second part, the next one, is that the function's values or terms are represented by this notation, a sub 1, a sub 2, a sub 3, and so on till a sub n. All right, let's take a moment and talk about this. A sub 1 just means the very first term, hence the 1. A sub 2 just means the second term in the sequence, or a sub 2. A sub 3 just means the third term up until a sub n, which is the nth term, or a term that we define. If I wanted the 75th term, then this would be 75. All right, infinite sequences. So what is a finite sequence? Well, a finite sequence is just like an infinite sequence, except its domain is restricted to the first n positive integers. So I could say, I could give you a sequence and it would be infinite if I didn't say anything, or if it was finite, I could say where n is between the third and the 18th number. Then we're only talking about 15 different terms if it's from the third to the 18th number. Cool. So let's take a look at some of the simpler versions of sequences, and let's look at recursion formulas. So recursion formulas are specific types of sequences where each term is found by using the value obtained in the previous term, so by the previous term. So usually they look like this. Now this one gives you the first term. It says a sub 1 is 5. So the first term is 5. And it says for every one after the first term, this is the formula that we use. That looks really intimidating. But remember, notice the first term again is given. A sub n is just the formula for all the other terms. So to find them, we look at this part. Now this is the one that looks a little confusing, a sub n minus 1. This just means the value of the prior term, or your previous answer. All right, so let's take a look at this. To find the second term, all we do is plug in a sub 1 for a sub n minus 1. So you see I have this. So if I want to find the second term, I have a sub 2, which is what I have here, 3 times this number. And that's just the previous value, which was given to us, which is a 5. So I have 3 times 5 plus 2. This is a simple problem. It looks intimidating because of the notation and the way that it's put together. So really, 3 times 5 plus 2, that's 17. So I'm going to plug that in as the value of the second term to find the third. So you see here, instead of having a sub n minus 1, the previous answer was 17, so 17 gets plugged in. Sweet. So this is easy to solve. It's just 53. And I use this answer and plug it in to find the fourth term, which is 161. So now I have the first 4 terms. It was asking for the first 4 terms. So first 4 terms are 5, 17, 53, and 161. Excellent. So again, a recursion formula uses the value of the previous term. That's what this means, the value of the previous term, just to obtain the value of the current term that we're looking for. All right, so let's take a look at your turn. Again, I give you the first term, which is 3. I give you a slightly different formula for all of the other terms. So let's find the first 4 terms. So go ahead and pause the video, and I'll be right back and check your work. And we're back. All right, so if you got these as your next 3 terms, then the first 4 terms are 3, 11, 27, and 59. Excellent. All right, so now we're going to take a look at factorial notation. And at the beginning, this looks super duper 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 complicated, but it's not. N factorial, the exclamation mark, is the factorial operator. Just means I'm going to multiply it times every factor 1 less than itself until I get to 3, 2, 1. You're like, what the heck does that mean? Why are there so many n's? Okay, just multiply by itself, multiply itself by each integer less than 1 less until you reach the number 1. So by definition, 0 factorial is 1. Let's get that out of the way. And now let's take a look at an example. Okay, so what this means is I have 4 factorial. That's 4 times 3 times 2 times 1. So you see I'm just subtracting until I get to 3 times 2 times 1. I'm just subtracting one number less, and 4 times 3, 12, 12 times 2, 24. 24 times 1 is 24. Perfect. All right. So let's use this to find the values of a sequence. So I have the sequence, the definition, the function for the sequence is a sub n is 20 divided by n plus 1 factorial. So if I want the first term, 1 plus 1 is 2, which is why I have the 2 factorial down here. Well, 2 times 1 is just 2, so 20 over 2 reduces to 10. All right. So if I wanted to do the second term, 2 plus 1 is 3, so you would expect to see 3 factorial, which we do. So 20 divided by 3 factorial is 20 over 6. This reduces to 10 over 3. So the next term, again, to the third term, I'm just doing 3 plus 1, which is why I have 4. We already know what 4 factorial is 24. 20 divided by 24, I just simplify, 5 over 6. And of course, for the fourth term, I have 20 over 5 factorial, and so that's going to be 1/6. 5 factorial, and then I'm going to reduce it, just becomes 1/6. Excellent. Cool. So factorial just means multiply again by every integer 1 less than the starting one. So multiply 4 times 3 times 2 times 1 until I reach 1. All right, so how can I make this a little bit more interesting as I see my first 4 terms in the box? So let's evaluate this one. All right, this looks really intimidating, and at first you want to just pull out your calculator and start multiplying. If you do, you will overflow. A lot of times some of the simpler calculators will just overflow and give you an error. Or so you'll start seeing things in scientific notation. Let's not do that. Let's see what 14 factorial means. All right, so 14 times 13 times 12 factorial, right? I have a 12 factorial in the denominator. These cancel. So now I'm just left with 14 times 13 times 2 factorial, which of course is 182 divided by 2, or 91. So look to see if you, especially if you see a bunch of numbers in factorial notation, if you can cancel out part or sum of that expression. So if you look at checkpoint 4b, I give it to you only in variables. Now recall that n factorial is n times n minus 1 factorial. These cancel. Oh my gosh, just n. Sweet. So let's try these. What would this cancel to? So go ahead and pause the video and see if you can do try C. And now that we're back, if you got this and we are expanding the numerator and the denominator, you see there's a lot of things that cancel. That leaves you with 3 over 16. The 2 factorials cancel out. The 15 factorials rather cancel out. Excellent. Here's another try. All right. I know it's n plus 1, but don't worry. Don't get excited. It is right there. If you pause the video and you're back, you know n plus 1 factorial is just n factorial, and you see these cancel out. N minus 1, so if it's factorial, you know that I just subtract 1, so that becomes n plus 1 minus 1 is just n factorial, which is where I get these to cancel. And of course, my answer is just n plus 1. Sweet. Factorial notation. All right, let's use summation notation. This is another operator. So now we've done recursion formulas, we've done factorial notation, and now summation notation. So summation notation is a way to shortcut and express all the terms of a sequence and how they're obtained. So this is what it kind of looks like. Let's dissect this monster. All right, this n. At the top of your sigma, this just means where you stop. So that's the integer where you stop. Now at the bottom here, I equals 1, that's just where I start. Now if I equaled 3, then my first term would be a sub 3. That's it. Or I would equal 3. I'm sorry, I would equal 3. And we just keep on going until we reach the nth term where we stop. Okay. Now we just add all those together until we reach a sub n, which is where we stop. Sweet. So for example, let's take a look at this one. Now I'm going to start with I equals 1, and I'm going to stop when I get to 6. So here you see I substitute in for I squared, I got 1 squared. And this is just all of the positive integers. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6. Why stop at 6? Because here it tells me to stop at 6. So I simplify each of these, 2 plus 8 plus 18, 32, 50, and 72. And that allows me just to add them together. My answer is simply 182. Sweet. Okay, so really not that difficult. It's just another way of shortcutting a long sequence of an addition problem or a sum. So why don't you try these? Again, I change it to a K, but it shouldn't matter. Remember, where do you start and where do you end? If you pause the video, you're back. Here you go. Yep, you just substitute in the values for 3, 4, and 5. Excuse me. And simplify, and we got 47. Let's take a look at example 3. Now, see if you can do this on your own. Now, what's confusing is I have no I here. But how many times am I going to add 4? That's right. Nothing changes. I just have 5 of the number 4. I add them together, and of course, I get 20. That, ladies and gentlemen, is sequences and summation notation. Simple, straightforward. Take a look at this video and review it if you have any questions.